All right, now what do we have to do today? We have a lot. We have the sample midterm. It's going to take a while. In the meantime, though, let me go back to Moodle for a second. I think it's open here somewhere. Let's see. Or it was. All right, let me get it. Here. Let's try. All right, here we go. All right, so there's our sample midterm. We'll be doing that in a minute. I posted chapter 9, which we will not obviously start today, but possibly tomorrow. And depending on how far we get with the sample midterm, I'm guessing that it'll take the entire period plus a little bit of Wednesday as well. But once we get through it, then I'll post the actual midterm. And then, look, I think we discussed yesterday, you can have a week to do it. I also had to make a correction to the chapter 8 notes. There's an example way at the end about proportions, which had a mistake in it. So if you open this up, you'll see that that correction has been made. It was just that one example. I had a typo or something, and then, oh, well, it was one of those things. Once you make one mistake, it tends to spiral downward. But yes, this very last example about proportions, there were some problems with it, so I fixed it. Okay, so when we get to this chapter, we'll be reviewing this for the final course, and we'll go over this at that time, but it's here now. The corrected version is posted. It actually says the word corrected in the title, so that way you know what that's all about. Now, also, I've gotten through the chapter 3 problem sets. They're all corrected. You should be able to see your grade in Moodle, but what I would like to also do is post the solutions so you can double check your work. I'll take care of that later on today, and then I'll do chapter 5, and then of course you're handing in 6 and 7, so I'll take care of those as well. But as at the moment, only the chapter 3 problems are corrected, but that will change very soon. Okay. All right. So in the meantime, let's get back to what we were about to do, which is to look at our sample midterm. Let's get this open. Now, there's a lot here because, of course, this is 4 chapters. 4 chapters is a lot for statistics. So, but since it's a very short summer session, that means that we have to hustle a bit. This is normally, like I said yesterday, there would be 2 midterms and a final. But that wasn't really practical. So by having 2 tests, it's a lot more work for each one, but you'll be doing this at home anyway, so it's not as big of a burden as it would be in the classroom. So I'm hoping that this will be very straightforward and you'll have no problems completing your sample, your actual midterm. So in the beginning, you'll see here that you've got, now fill-ins are short answer questions. These are questions that can be often answered with a few words, maybe a sentence, maybe a number or 2. These are not full-blown problems. I usually start with those. And so here, this is simply a list of the topics that we've actually covered. And when you look at this list, you'll see that's a lot. We've really gotten through a lot of material in just a matter of 2 or 3 weeks. So then we start with the actual fill-in questions. Okay, so there's 20 of them. And like I said, in many cases, you'll be able to answer them very quickly with just a word or 2, or maybe a full sentence. In other words, you should not need to write more than that because they're meant to be very, very short. Then we dive into the actual problems. And this is where all the hardcore math gets involved. All the problems we've been doing are here somewhere. Pretty much we covered everything here. So, all right, I guess we'll get started now. Let me just save this real fast. We're going to put in all the answers now. Today's the 22nd. And so this way you'll be able to have this in front of you along with all of your other notes and materials while you're taking the actual exam. All right, good. So let's start at the beginning. So there are 3 axioms of probability. What are they? Okay, so now something like this. I mentioned this before. The first 2 are pretty self-explanatory. The first one is essentially telling us that no probability can be negative. At the same time, though, the probability, and by the way, if you notice, I'm not typing out all the words. This is enough. This is good enough. There's a lot of discussion here about what this actually means. But if you just write this for number 1, number 2, you can write the probability of the sample space equals 1. That's all you need. Okay. You can write more if you want to, but this is all that's really necessary. Now, number 3 is a little bit messier. You do have to mention in this case that the events that we're describing are do not overlap. Okay, so for 3, we should put a little English in here. What the hell is going on? Hold on, hold on 1 second. I don't know what's happening. Oh, here we go. Okay. So for number 3, we do need to add 1 key detail for any collection of disjoint events. And that simply means they do not overlap. And then you can write out the full statement. The probability of their union equals the sum of the individual probabilities. And this is basically an extension of the simplified addition rule, by the way. The simplified addition rule is this applied to only 2 events. If we had a third disjoint event, then we could add up the probability of their union would simply be the sum of the 3 individual probabilities. So that's really what this is telling us. This is justifying the simplified addition rule. All right, so those are the 3. And if you wrote those words down, you're all set. Now, how about this one? What conditions must be met for 2 events to be independent? All right, so for any events A and B, 2 things have to be true. Okay, the probability of A given B must equal the probability of A, and the probability of B given A must equal the probability of B. It has to be both. One is not good enough. And the whole logic here is that the outcome of B doesn't affect the probability of A and vice versa. They just do not affect each other. Okay. We did an example, I think we talked about the case where we were looking at the Dow Jones and rain or something like that. They don't relate to each other. So therefore, they're independent. The correlation coefficient has to fall somewhere between -1, +1. Okay. That's all that we can have. In fact, it's defined that way on purpose to make it easier to understand what it means. All right. Nice. Okay. Now, if a sample is negatively skewed, now remember when we did this, we had 3 cases, negatively skewed, symmetrical, and positively skewed. This is the one where the mean is the smallest of the group. Which is then turn less than the mode. In other words, the mean is the smallest, followed by the median, which in turn is followed by the mode. And if that happens, we have a negatively skewed sample or population. And if you remember, that looks something like this. We use histograms, but you can do this with a continuous curve as well. It typically looks something like this. So it's got this long left tail. These are all typically negative values. All right. So by the way, you can see that these are indeed very short answers. They typically don't take it. This one was a little longer because there was 3 axioms, but other than that, they're just short answers. That's really all they are. So here, an event is a subset. I'm going to put that word in italics because it's so important. All right, that's it. That's all you have to say. Now, what about complements? Now, remember, we just got through seeing what has to be true for 2 events to be independent. This is a little bit different. Their union must be the sample space, and their intersection must be empty. Now, you can also write it slightly differently. If you're using probabilities, you could demonstrate this in the following way. Either one of these is fine. Okay, and in fact, in some cases, the one on the right is the only information you have, and you'll have to use that approach. It depends on whether you know what elements are in the sample space and what elements are in A and B. Sometimes you don't have that information. So, but either set, the one on the left or the one on the right, to combine is enough to prove whether or not 2 events are complements. All right, if A and B are mutually exclusive, what is the probability that both of them are true? Hold on 1 second. That both of them will occur, and the answer is 0. Because that's what it means. They can't both be true, so therefore the probability of both of them is 0. Okay, when do we use the simplified multiplication rule? When the events are independent. Okay, independent of each other, and then we're allowed to use the simplified multiplication rule. Okay. All right, 9. Suppose an experiment consists of choosing a single card from a deck. A is the event that the card is red. What would be the complement of A? So A complement, which is A with a little c, would be the event that the card is black. Okay, how do we know this? Now, it doesn't ask you for an explanation, but this is true because all the cards must be either red or black, and no card is both red and black. So I thought I'd throw that in there for a little helpful explanation, but all you have to say is that the event is that the card is black. All right, nice. So when is the simplified addition rule used? This is used when the events are mutually exclusive, meaning that they both cannot be true at the same time. Okay, now we're on to a different chapter here. What is a discrete random variable? All right, so discrete random variable assigns numerical values to the outcome of a random experiment in such a way that there are only a finite number of possible outcomes. Or actually, let me simplify that a little. Where the number of possible this is a little cleaner, I think. The number of possible outcomes is finite. That's better. Like flipping a coin 10 times, for example. X is the number of heads. It can only have a value from 0 to 10, which is a finite number. And then the continuous is the opposite case. A continuous random variable assigns numerical values to the outcome. Actually, it should be outcomes, shouldn't it? Yes. Outcomes of a random experiment where the number of possible outcomes is infinite. That's it, just the opposite. Like the time until the next phone call or something like that. All right, which probability distribution is based on a series of independent trials? The binomial distribution. If you remember, this is one of the three requirements for our binomial distribution: independent trials, only two possible outcomes, and constant probability of success. Now, this one's a little tricky. For which probability distribution are the expected value and variance equal? Well, if you recall for the Poisson, the expected value was lambda and the variance was lambda. So that's why the correct answer here is the Poisson. Okay, so it's a bit of a trick question. But since we only know three probability distributions at the moment, you could have gone back and looked at the formulas and said, well, what's going on here? Are there any cases where the expected value equals the variance? And the answer would have been yes, only with the Poisson though. All right, now what are the two values that uniquely characterize the normal distribution? Well, we've already went through this, but let me remind you that that would be the mean and the standard deviation. All right. Once you know those two items, you know everything you need to know about the normal distribution. Now, the standard normal, remember, with the standard normal distribution, the mean is 0 and the standard deviation is 1. So since sigma, the standard deviation, equals 1, then the variance must also equal 1. Okay, in other words, what we're saying here is that since the standard deviation is 1, then if you square that to get back to the variance, that one also has to have a value of 1. Okay. Okay. Which probability distribution can be approximated with the normal? Well, we saw the binomial, although I did mention that you can also use the Poisson this way. But let's just stick with binomial because we actually did that one. Now, the variance of the binomial random variable is, let's see, you might recall that it was equal to n times pi times 1 minus pi. It was one of those shortcut formulas. Remember, all the distributions have shortcut formulas or their own unique set of formulas for the moments. Okay, we have the general formulas, of course, but each of our probability distributions, like for example, binomial and Poisson, has its own set of shortcuts for these moments. All right, now, what about this one, lambda? Now remember lambda, I guess I should have written in the Greek letter. Lambda is this guy. Let's see if I can find it. Yeah, there we go. In the Poisson distribution, so lambda represents is the average number of events that occur per unit of time. And that, of course, has to be given to you in the formula. Now here, what formula is used to convert a normal random variable into the standard normal form? That's this thing. Okay, that's what they're referring to here. Now, let's take a look at these problems. Now, you recognize these right off the bat from chapter 3. We're going to calculate all these measures. So let's start with the mean. And we'll observe that this is a sample. Add them up. Divide by 6, because we have 6 elements in the sample. So we'll have 12 over 6, which is 2. All right. So how about the median? Now, of course, what we're going to do here is sort the numbers from low to high, like we always do. And when we do this, we get -1, 0, 1, 3, 4, and 5. Now what do we do? Oh, that's right. It's the median. So since there are 6 observations, with an even number of observations, we will take the average of the 2 observations in the center. And so that would be all right, let's try that again. Okay, so we're looking for these 2. I'll just use italics, I guess. And so the median would be 1 plus 3 over 2, which is 2. Okay, so in other words, it's halfway between the 1 and the 3. All right, and then the mode. Well, there's no mode because there's no repeated values. There's no mode. All right, now the third quartile, we've got an even number of values. And we know what we typically do here is split this up into 2 halves. And the third quartile is the median of the larger, I guess, group of values. So in other words, what we're looking for, we split up the data into 2 halves, and then we look for the median, and that would be 4. Okay. All right, so the third quartile is 4. All right. Now, how about the range? The range is easy because all we have to do is take the largest and subtract the smallest. 5 minus 1 equals 6. That's nice and easy. Now, for the interquartile range, we need Q1 and Q3. So we already know the value of Q3. So Q3 minus Q1, but we already know Q3. So if we come back up here and copy these numbers again, we can easily find Q1, or the first quartile, is actually going to be the median of the smaller group of values, which is 0. All right, so this time you're selecting this value, and then we subtract 1 from the other. Oops. And so our final result is, before we had 4 for Q3, now we have 0, and so the final answer is simply 4. Okay. Very good. All right, now the variance. Now this is where it gets a little more challenging. What do we need to know? Well, first let's repeat the formula here. I'll just move this down here so I have more space. And I'll just grab the numbers. And a quick reminder that the mean that we determined earlier was 2, okay? So the sample mean is 2, X bar is 2. That's an important detail because we need it for our formula. So remember, this is a sample. And oh, one more thing we should note here, N is 6 observations. So what we have to do is go through every element in our sample, subtract the mean of 2, and when we're done, we add them up and divide by not 6, but 5. All right, so let's see if we can fit this all in one line here. And in the denominator again, we have 6 minus 1 because it's a sample. Now, of course, we have to evaluate it. So let's do it this way. Minus 3 squared plus minus 2 squared 3 squared, 1 squared, minus 1 squared, 2 squared. Okay, and then we'll end up with 9 plus 4 plus 9, 1 plus 1. All right, and that adds up to 28 fifths, 28 over 5. Yep. Which is 5.6. That's our variance. All right, so let me give you a second to catch up with that. And then the standard deviation would, of course, just be the square root of that. Oops, sorry, S right there, not S squared. Um, 2.366. And then now the coefficient of variation, if you recall, is equal to the ratio of the standard deviation to the mean times 100 to turn it into a percentage. And so we've got 2.366 all right. And so that ratio is approximately equal to 118.3%. Very good. All right. So that's a nice thing about some of these. Once you've got 1 or 2 of these numbers, you can get more of them very simply and easily. All right. Now we're ready for problem number 2. Now this one is a little bit different. An investor buys a stock and holds it for 50 trading days. The following table shows the daily returns and their frequencies during this period. Okay. So as soon as you see this kind of thing, you should immediately think weighted average, all right? How do we know that? Because the returns are repeated many, many times within the sample. So in other words, we lost 2% 10 times, we lost 1% 12 times, we broke even 14 times, we made 1% 8 times, and we made 2% 6 times. So when it says, what is the average daily return during this period? What they're actually asking you to do is construct a weighted average. All right, so in other words, since this is a sample, although the actual calculations are the same in this case, whether it's a sample or a population, all right, and also the frequencies are the weights. The X is the value of interest is the returns. So don't get that confused. The frequencies are the weights. So we're going to have, we'll go through the list. 10 times negative 0.02. Also, don't forget to convert these into decimals. 12 times negative 0.01. 14 times 0. 8 times 0.01. And 6 times 0.02. And then we add up the frequencies or the weights. Okay, so then if you take out your calculator, you'll see let's see, this is 0.12. That would be 0.12. The frequency should add up to 50 because there's 50 days in our sample. Let me just double check that with my calculator. I want to make sure I didn't make any mistakes. Uh-oh, I didn't notice these chats, sorry. What is the difference? I apologize, I didn't even see those questions. I was so busy with this. What's the difference between independent and mutually exclusive? Okay, so let's stop right here and answer these questions. I apologize that I didn't see them earlier. Here's the difference. Mutually exclusive events can't both be true. For example, A is the event that, suppose that we pick a number is chosen. Or how about this one? A roulette wheel is spun, a pretty cool example. Now, just that, if you recall, the roulette wheel has numbers from 1 to 36 and 0 and 00. So A is the event that the spin is an even number, and B is the event that the spin is an odd number. Is it possible for both of these to be true? No. Okay, it is not possible for both A and B to be true. Okay, the number you pick, it's either even or odd. There's no such thing as a number that can be both. So therefore, A and B are mutually exclusive. And you can write that in math terms as the intersection between these two is empty. Or you could say that the probability of the intersection is 0. Both of these imply that A and B are mutually exclusive. Now, independent events are different because independent events, they can both be true, but what's important here, do not affect each other. So let's say that we observe, let's see. Oh, how about this one? We observe the weather in New York and LA. A's event, it rains in New York. B's the event that it rains in LA. Now, if I said New York and Boston, now you know they're close enough to each other that the weathers, they can both have miserable weather at the same time caused by the same weather front. But New York and LA are so far apart that the weathers in the two cities should be independent of each other in the sense that while it can rain in both cities, the fact that let's say the following two things can be said to be true. The event that it rains in New York has no influence on the probability that it rains in LA. And the event that it rains in LA has no influence on the probability that it rains in New York. So let's just say you're following baseball and you know that baseball games get rained out during the spring and the summer fairly often. So if you're concerned that your team might not be able to play tonight, You might say, well, the Yankees are in Baltimore. Oh no, it's raining here. It might be raining in Baltimore. So those are not independent events. But if it's the Yankees playing in the Angels in LA, the fact that it's raining in New York doesn't affect the probability that they could get rained out in LA. So it just means that the two events do not influence each other. And so how does that manifest itself? We saw that earlier. All right, so in other words, knowing that it's raining in New York does not affect the probability of raining in LA, and knowing that it's raining in LA has no effect on the probability of it raining in New York. All right, now the second question is this coefficient of variation versus the sample covariance. Okay, so the coefficient of variation is equal to standard deviation over mean times 100. It is a measure of relative risk, or relative dispersion would be more general than that. It's technically a measure of dispersion, but it is also taking into account the spread as well. Whereas the covariance, the sample covariance, which looks like this, let me just quickly review with you the formula, and then we'll remind ourselves what it actually means. Okay, the sample covariance is a measure of how closely related X and Y are. Okay, so we often call this a measure of association. And that's an attempt to tell us, like, is it the case that X and Y tend to go up at the same time, down at the same time? Yes. So the third question is not a question. This is quite correct. That Mekhala has correctly said that the coefficient of variation is in fact standard deviation over the mean times 100, and the sample covariance is this term. Okay. All right. So now I think we're all caught up. So I'll have to keep my eye open more for these questions. I don't know. I guess even it flashes orange for like 2 seconds and then it stops, which is kind of unfortunate. That's why it's easy to overlook them. All right, so I hope that was helpful. Now let's get back to this. Oh, yes. So yes, this is correct. And so when you divide that out, you're going to get 0.0 negative 0024, which you could rewrite if you choose to do so as negative 0.24%. Okay. Okay. So now the correlation, now we're going to actually do the covariance and the correlation. So first things first, we need to calculate the sample means, okay? All right, so what is that? That's 10/5 or 2. Okay. And then for the y's, We have, oops, sorry, what did I do? It's not 8, it's 5. Okay. So we'll go ahead and apply it now. We just got through, I reviewed that formula with you a second ago, so let's go get it back. This is what we have to do to get the covariance. Okay, so what I'm going to do is copy the numbers back so we have them down here. All right, and also don't forget, so X bar is 2, Y bar is 4. All right. So let's put these in here. Now this is going to be it's probably going to spill over multiple lines. Let's see what we can do here. So basically, just keep in mind, what are we doing here? We go through these rows one at a time. So I start with these two. I subtract X bar from this X1. And I do the same thing for Y. This is now Y1 minus Y bar. And then the second term, I move down to here. So for the X, I have 0. And I always subtract 2 because that's the mean of X. And then over here for the Y, I have 5 minus 4. And again, I'm always subtracting 4 because that's Y bar. And I keep going down the list. And as I figured, there's no way I can fit all that in one line. So let me keep going. Two minus 2, 7 minus 4. And then finally, we'll have 7 minus 2 and 1 minus 4. All of that is divided by 5 minus 1 because it's a sample. Wow, what a headache this is. So let's write them all out individually before we do anything else to minimize the risk of mistakes. And again, now we're dividing by 4. $15 minus 2 plus 4. Okay, so we've got 2 over 4, which is a half. And because it's positive, that indicates that there's some tendency for the two variables to move in the same direction. We don't know how strong that tendency is, but we do know that it's a positive tendency. All right, let me leave it there for a minute so you can catch up. Now, for the next part, we're doing the correlation, which means that we have to unfortunately do 2 standard deviations before we finish this problem. Yeah, I know it's going to take a while, but we have to do it. It's also good practice. All right. All right, so I'll tell you what, let's go get the, oh, here they are. That's easy. I just want to copy these again so I can see them. And again, a quick reminder that X bar is 2. And Y bar is 4. And further, the standard deviation formulas. Now, we don't normally use subscripts here, but we do here because we've got 2 different samples. Okay, so we'll plug in the numbers. Now, what we typically do with these cases is we calculate the variance first, and then we take the square root at the end. So let's do it that way. It might be a little simpler. So I'll start by calculating the variance. And of course, what I'm actually doing is going through all the x's only, subtracting the mean, but now I'm squaring them. Also, don't forget, since this is a sample, we're dividing by n minus 1. Okay, let's plug in these numbers. +25 plus 4 plus 4 plus 0 plus 25. Oh, what did I do here? Sorry, this is not 4 minus 1, it's just 4. All right, that's better. All right, so the variance of x is approximately equal to, well, it's exactly equal to 14.5. So we still have to take the square root. And that's about 3.808. All right, so that's done. Now we get to do the same thing for y. And then finally, we'll be able to calculate our correlation coefficient. Okay, let me go grab the numbers again. All right, so let's do the variance of y first, and then we'll take its square root. So we'll go through all the y's and subtract 4 in each case because that's y bar. Oh, no. Okay, hold on one second. Sometimes when the document gets big, it becomes a problem saving it. But I think I know a workaround for it. No. Um, all right, hold on 1 second. I have to do some housekeeping here. The computer, no matter how powerful you think your computer is, there's always a problem with it. So I'm just going to have to break it up into little pieces. That's all right. It's just so, annoying that this is even necessary. All right, it accepted that one. All right, now. All right. I'm still, don't worry. I don't want to waste all day with this, but I don't want to lose my work either, which could happen if I don't attend to this right away. I know it's happening. There's too much memory in this thing. No. All right. No, it's still wrong. Let's see. All right, I'm almost done here. No. I think I'm just going to have to do this part all over again. It's really being a pain in the butt. All right, so you know what? Let me just quickly run through this again. I'm going to do the standard deviation for this one again because it wouldn't save it. So let me just quickly go through that, and let me just do one more check. Just making sure nothing's lost. Okay. All right, so I'll just quickly run through this, and we have to do y as well. All right, and then we divide all that like we did before, 5 minus 1. Wait, hold on. All right, so we had a 58 fourths or 14 fifths, 14.5. And then, of course, we have to still take the square root. Great. Now, let's see if it'll let me save this. And then we can do the standard deviation of y. No, it actually let me save it. Isn't that nice? All right, so we'll do y now. And it's the exact same procedure, but you might remember that the mean of y is 4. So we'll use this data right here. Now let's just copy all this. All right, we don't need that anymore. So, all right, for y, we'll start by calculating the variance of y. So we go through all the y's, subtract 4 in each case. And again, we divide by 5 minus 1 because it's a sample. Okay, so we have 9 plus 1 plus 4 plus 9 plus 9 over 4. It's exactly 8. And so the standard deviation is the square root of that. Which is about 2.828. 2.828, that's fine. So what do we know? We'll gather up all of our information. First of all, the correlation coefficient is the sample covariance over the 2 standard deviations. So, not 2, 0.5. And then we just got through showing that the 2 standard deviations are 3.808 and 2.828. And when you multiply that out, you'll get approximately 0.0464. So it's very close to 0. These two the two populations are more or less independent of each other. Okay. So that nightmare was number 3. And so now okay, so we're going to carry on with this one. I'll give that one a new name just in case it blows up on me again. All right, now here we're doing probability theory, so it shouldn't be quite, we shouldn't take up as much space, so we should be okay from now on. So what do we have here? We have an experiment where we flip the coin 3 times. A is the event that at least one head turns up, and B is the event that at least 2 tails turn up. All right, very good. So what you should always do is make sure you know what the sample space is. If you're not sure, you can draw this little binary diagram. We can show that after one flip, either you would have to get a head or a tail, of course. But after the second flip, if the first flip was a head, you now have head, or head, tail. Over here you have tail, head, tail, tail. And then if you had 2 heads to start with, the next flip can be a head or a tail. Here you have HTH, HTT, THH, THT, TTH, and whoops, I wrote it wrong. This should be TTH and TTT. Now, what I prefer to do here is write out the sample space in a specific way, not this order that you're seeing here. What I think is the most convenient way is to put all the cases first where there's 3 heads, and then all the cases where there are 2 heads, and then all the cases where there's 1 head, and then save for last the case where there's just 3 tails. Wait, no, that's not right. This one is not right. That's better. Okay, so in other words, if you notice what's going on here, there's 3 heads here. In each of these 3 cases, we have 2 heads. And in each of these 3 cases, we have 1. Oh, no, I still screwed it up, didn't I? No, I'm sorry. These are not right. Let's do these all over again. I need now the ones where there's 1 head. So HTT, THT, TTH. That's better. Okay, now we're all set. In other words, I guess I could have just left them in that order, but I like it this way because it's easier to identify the events. Let's just make sure we didn't miss one of them. Yeah, that'll do it. Okay, because if you get the sample space wrong, every one of these questions will be wrong. So we have to be really careful with this. Okay. That's better. All right, perfect. So now the first question, oh, and also A is at least 1 head. That means 1 or more. So basically, you're including everything except 3 tails. So you see, that made it easy to identify A because of the way we set it up the sample space. B is at least 2 tails, which means 2 or 3 tails, which means all of these cases down here. Now, once you have those done, these are easy. Now, remember, all of these are equally likely to turn up. So for example, with the probability of A, all you have to do is note that there are 7 elements in set A out of 8 total, which means the probability is very simply 7/8. All right, that's all you have to worry about. Just count them. For B, we do the same thing and we get 4/8. Now, with the union, this is a little bit trickier. You could use the addition rule here, but it might be quicker and easier to simply note what elements belong to this union. And if you look at them very carefully, you'll see that every element is in either A or B. So in other words, their union is the entire sample space. So they're all either in A or B or both. And we already know that the probability of the entire sample space is 1. Therefore, this probability must also be equal to 1. All right. Or see what I mean? You can just say, well, the union is all these elements, and if you count them, you'll also get 8 out of 8. Okay, so anyway, look at it, you're getting 1 for your answer. Now, what about the intersection? That's a little trickier. We have to figure out what do they have in common. Let's find out. Why don't we do this? Let's copy the elements down here and see where they overlap. So it looks to me like they both have all the cases with 1 head. And that's it. These 3. Okay, so they overlap by 3. So the intersection between them is the set HTT, THT, and TTH, which implies that this probability is simply 3 out of 8. because there's 3 elements in the set, and there's 8 in the entire sample space. Okay. Now for the complements, these are easy because we can just use the rule. So remember, A had a probability of 7/8. When we subtract, it's up here, yeah. We subtract it from 1, very easy. And then here we have 1 minus 4/8, which is also 4/8, or 1/2. Now here it gets interesting because you have to use the definitions. But we've already calculated these. The intersection between A and B, as you recall, had a probability of 3/8, and B had a probability of 4/8. So this can be rewritten as 3/8 times 8/4, and that leaves us with 3/4. Okay. And then for this one, we have the same concept. The only difference here is that we have A in the denominator, the probability of A. So we're taking 3/8 and dividing it by 7/8, or 3/8 times 8/7, which is 3/7. All right, and then we have 3 conceptual questions, which are pretty straightforward. Are A and B mutually exclusive? Why or why not? Well, there's a few different ways you can express this. No. Their intersection does not have a probability of 0. Their intersection is not empty. So by the way, you only need one of these. A and B have at least one element in common. Any of these will do. You don't need all 3. Any one will do. You pick the one that makes the most sense to you. Now, to demonstrate independence, remember we need 2 things to be true. Now, just a few minutes ago, we showed that the probability of A given B is 3/4, but the probability of A is not 7/8. So since this condition fails, we do not need to test whether or not the probability of B given A equals the probability of B. We know A and B are not independent. Okay, and lastly, for this one, complements, we need to show whether or not the intersection is empty and their union is the sample space. Well, this one is true, but this one is false. So therefore, it doesn't matter that the second one was true, since at least one of these conditions is false. A and B are not complements. I didn't miss any more questions, did I? No, good. All right, so we've got some more probability theory coming up here. I see it's time for our morning break. We've got probabilities and then more probabilities. And when all that's done, we can do random variables. So I would mention before, I don't believe that we'll be able to finish this today. It's fine. There's no rush, but we'll probably finish this fairly early tomorrow. And when we're done with it, then we can dive back into chapter 9. All right. So, if we don't finish this today, it's not a big deal. So, but because there's a lot here. All right. So after the break, we'll stop. We'll pick it up with question 5. And all right, let's keep it going. So hopefully the computer will continue to let me save these documents, and I'll see you in a few minutes. All right, let's pause this. All right, let's get back to it. So this one's a little different. A card is chosen from a deck, the card is replaced, and then a second card is chosen. Now that's an important detail because that means that these events are independent of each other. So let's make a note of that right now. That'll come in handy. Since the card, first card was replaced before the second card was chosen, the two events are independent of each other. If not, of course, they would not be independent. Oops, I almost forgot to turn this thing back on. So yes, so we first note here that when the card is chosen from the deck and it is replaced before the second card is chosen, this is known as sampling with replacement, and that means that when we pick the second card, the entire deck is intact. Therefore, the events are independent of each other. So in other words, the probability that the second card is black does not depend on whether the first card was a king. Now, here's a quick reminder too, in case you've forgotten, a standard deck contains 52 cards, half are black, half are red. Also, there are 4 kings, half of which are red and half of which are black. So you don't have, I mean, the sample space is actually the entire deck, and each card is equally likely to be chosen. So those are important details. So I'll just add this as well. The sample space consists of the entire deck of cards, each of which is equally likely to be chosen. All right, that's another very important detail. So what about A? What is the probability of A? Well, remember what A means. The first card is a king. So there's 4 out of 52, and that's it. You're done. I mean, you can reduce it if you want to, but that is your answer. Okay, so in other words, if you want to simplify it to 1/13, that's fine, but it's not absolutely necessary. And for the same reason, B, the second card is black, is 26 out of 52, which is a half. Okay. So you can see these are kind of easy. Okay, so this is just using the complement rule. 1 minus 1/13 is, of course, 12/13. And this, we do the same thing for B. 1 minus a half is just a half. Okay, so you're good there. Now the probability, now A and B in this case means that the cards, you picked a king on the first card, and the second card, the card was black. Now this is where it gets interesting. Since A and B are independent, we can use the simplified multiplication rule. And so what you do here is multiply these together. In other words, the probability of A times B is 1 out of 13 times 1/2, which is 1 out of 26. Now, these two are kind of trick questions because since A and B are independent, this probability equals the probability of A, which we know is 1/13. And down here, since A and B are independent, the probability B given A is the probability B, which we've already calculated to be 1/2. Very nice. Are A and B mutually exclusive? No. Because we've already seen that the probability of A and B is not 0. It's equal to 1/26. Okay, are they independent events? Yes. Now here you don't have to prove it except to say that yes, because the cards are drawn with replacement. That's how you know in this case. All right. Are A and B complements? Good question. We have to confirm two things in order to show yes or no. So let's do it. In this case, we'll use this approach. Oh, bad luck. This condition already fell. So now the probability of A and B is supposed to be 0. And in fact, the probability of union B, which we haven't even demonstrated it, is not 1. We don't need it because we're already done. So the answer is no, because A and B are not mutually exclusive. That's it. That's all it takes. Okay. So that one was a little more straightforward, although it is important to recognize that the drawing with replacement guarantees that they're independent of each other. If you didn't remember that, you would have had some problems. Now, number 6 is even a little different because here we're not being told anything except for these 3 probabilities. We're not given the sample space. We don't know what these even represent, but we do have probabilities, so we should be able to answer these questions by using our rules. Okay, so this one, we know the complement rule by heart by now, I hope. So that one's 0.8. For B, 1 minus 0.5. Now the union here, we can use the addition rule for that. Okay, so the probability of A union B, of course, using the addition rule, is the probability of A plus the probability of B minus the probability of A and B, or 0.2 plus 0.5 minus 0.2, which is of course 0.5. Look how easy that was. Now for these two, we'll simply write out the definitions of conditional probability. So we know from up here that that's equal to 0.2 over 0.5. And then for B given A, so that's 0.2 over 0.2. So this probability is 1. Okay, now are A and B mutually exclusive? Why or why not? And the answer is no, since the probability of A and B Remember, it was 0.2 from up here. It's not 0, so therefore these cannot be mutually exclusive. How about independence? Now remember, that requires two things to be true. So we must check whether the probability of A given B equals the probability of A and B given A equals the probability of B. Well, A given B, we calculate up here to be 0.4. And A, if you recall, has a probability of 0.2. So clearly already we know that that's it. They're not independent. We don't have to bother with the second condition. And that's the reason. All right, and then complements. Again, there's two things we should check out. Whether or not the probability of A and B is 0. And their union is 1. Well, we've already seen that the probability of A and B is 0.2 from the top here. Therefore, oh boy, that means no. And so the result of this is that A and B are not complements. Okay. Now we've got a probability table, a joint probability table. These are pretty straightforward. We just have to apply the rules. So the first three are what we call joint probabilities. We can look them up directly in the table. So what's going on here? We have coffee from Starbucks, either decaf or regular in 3 styles: French roast, Guatemala, or espresso. So F and D means French roast decaf, and it's found at the intersection of F and D. Easy. R and E, regular espresso. It's found at the intersection of regular and espresso. Oops. 0.10. And then finally, R and G is regular Guatemala, which is found right here. So the first 3 are a breeze. All right, not that they're all not a breeze, but those are especially breezy. All right. F. Now, F is simply all of the French roast, the total. So, oops. Nope, that's not what I want. 0.46. That's the total for all the French roasts, regardless of whether they're decaf or regular. Regular, so read across, and that adds up to half the total. Fine. So it's half and half regular, half decaf. This D complement is 1 minus the probability of D, which is, now D, if you notice, is also 0.5. And that's a half. Now, F or G, now, just want to mention here, just in case you've forgotten, note the columns are disjoint or mutually exclusive of each other, as are the rows. All right, so in other words, you cannot have the same coffee being both French roast and Guatemala. It can't be both Guatemala and espresso. It can't be both regular and decaf. So if that's the case, then I can use the simplified addition rule for these unions. It looks like somebody asked a question and I didn't see it. Sorry about that. Oh, absolutely. As soon as we're done, it's going right on to Moodle. Yes, there's no question about it. That's why I'm spending so much time writing them out like this. Now, if we don't completely finish it, I'll just put what we did finish today. Now, as you saw, sadly enough, I had to break it up into multiple parts. So it looks like we'll for sure have the first 3 parts ready today. And this part And then whatever we don't finish today, we'll do tomorrow. Oh yeah, I know. This is a lot to keep up with. There's a lot going on here, and I know you want to go through it and review it and ask questions tomorrow if you need to, which you can always do. You can always just say, listen, I don't get number 3. What's going on with number 4? That's fine. Okay, it's not supposed to be a mystery. All right. There's no intention here of tricking you or deceiving you. If something doesn't seem right, just ask. Maybe I worded it funny or something happened. It's hard to write good questions. And occasionally I'll write it in such a way that maybe my intentions were not completely clear. So, just ask. There's not meant to be tricky. It's that simple. I'm sure you have had classes that were meant to be tricky and you were not happy about it, I bet. But anyway, so for these, the addition rule ones, you literally just add them up. French roast in Guatemala, you just add those up. Same thing with Guatemala and espresso. You'll end up the totals. Okay, so those are easy. Now the last 3, as you can see, are conditional probabilities. We'll use the definitions. Okay. Now DNF is decaf French roast. And F is, of course, French roast. So you got the totals here. So 0.18. Now, you could leave the answer like that if you want to. I'll accept that on a test, but I'm going to round it or calculate it, and it turns out to be approximately 0.3913. Okay, now for this one, all right, so R&E is regular espresso, 0.10, and then espresso is 0.32. So that ratio is equal to 0.3125. And then we finally have G given R. Let me leave those there for a minute. G given R. So that's regular Guatemala. And regular is 0.50, and that brings me to 0.24. Okay. So I think we're done with probability for now. Well, not exactly. We're moving on to probability distributions. Okay. All right, so let's go ahead and get ahead here. So here's a table. Now, this is not one of our defined probability distributions. This is not binomial. It's not Poisson. It is just some probability distribution. And you can see, number one, the question is this a valid probability distribution or not? And the answer is yes, for 2 reasons. Okay, each individual probability is between 0 and 1, which I'll write like this. And the sum of these probabilities equals 1. That's what it takes. They both have to be true, and they certainly are here. Part B, is X discrete or continuous? Okay. X is discrete because it can only assume a finite number of different possible values, specifically 3. 3 is, of course, a finite number. So there's only 3 possibilities. Therefore, X must be discrete. Oops, let me split the screen a little. Now, the expected value of X. Now, for something like this, there's a formula that you saw in this chapter. So the X's and probabilities will be multiplied together. Let's see. All right, I didn't think I was going to make it there. So if we add these up individually, you'll get 30 plus 150 and 100, 280. So the average value, the expected value is 280. And literally, it's just a weighted average of all the X's, where the X's, the weights are the probabilities. Okay. Now, what about the variance and the standard deviation? Well, the variance is, a little challenging, but the standard deviation will be easy because it's just the square root of the variance. So let's take a look at the variance. Now, remember, the variance formula is very similar to the one we use for populations and samples. So go to the X's. In each case, subtract the 280, is that the expected value, which is 280. Okay. Oops. All right, so let's see what that works out to be. Now, 100, that first term is actually 9720. The second term is 200. And the third one is 9680. And the grand total is 19,600. Okay. And now, of course, for the standard deviation, we just need a square root here. So therefore, we take the square root of the variance, $140. And that's it. All right. Now we're getting into the binomial Poisson's discussion. The next question is also about probability distributions, but it's a specific one. And you'll see why I say that in a second. We assume that M&M Mars produces a special bag of M&Ms at Easter time, which contains 40% purple and 60% pink M&Ms. So there's only two colors. That gives you a hint that we're now dealing with a binomial distribution. Let's just say arbitrarily pick purple to be the success and pink will be the failure. We pick 4 M&Ms at random. So we have 4 trials of this experiment, and we'd like to know the following probabilities. So as far as our notation is concerned, n is 4, and pi, the probability of success, is 0.40. Now for these, you can choose to use the formula, or you can use your calculators. So let's do it both ways, just to make sure we get it. So here, the probability that x equals 0. While we're at it, I might as well write down the full formula again. Okay, so plug in these numbers. All right, so you notice at pi is 0.4, which means that 1 minus pi is 0.6, n minus x is 4. Now it turns out that if you put these into your calculator, this first term is 1, as is the second term. The third term is the one that gives us the actual value, which is 0.1296. Okay, so 1296. Now, if you're using your calculator, what you have to do second, as usual, second VRS, binom PDF. Make sure it's PDF. And when you get there, it's going to ask you for, hold on, let me go get it open. Oh yeah, trials. The trials are 4. Key, the probability of success is 0.40. And X value is, in this case, is 0. And if you plug in those numbers, you should get the same thing. There could be a rounding difference, 0.1296. This time it's exactly the same. All right. So it's up to you to decide which one you want to use. Okay. Now for one purple, we'll go through the same thing. Now, don't forget, n is still 4, pi is 0.4. But in this case, x is 1. So we have pi to the 1 power, 0.6 to the 3rd power, because that's n minus 1. So those first two terms are easy, 4.4, and 0.6 is raised to the 3rd power, 0.216. Okay, we multiply that by 4, and then by 0.4, 0.3456. All right. And again, with the calculator, let's steal all of this. The only thing you're changing is X. So change your X, that to a 1. Go back to the calculator and start again. And you'll see, let me just double check mine, that it gives you 34, exactly 3456 again. Very unusual that they're an exact amount like that. Now, the third one is a trick question, kind of. At least one purple. Or what? Let's write it as this: X is greater than or equal to 1. So it turns out, and we did go over this once, this is the same as 1 minus the probability that X equals 0. So in other words, at least 1 and none are complements of each other. And you can see why, because they cover all the possibilities. Now, just before we calculated the probability that X equals 0 as being 0.19296. So it's 1 minus 0.1296. And so when you subtract, you'll get 0.8704. Now, the other option, now remember, we only chose 4 M&Ms. You could have also just done X equals 1, 2, 3, and 4 and added them up. There's no point, though, because this is so much faster. If you did it that way, that's fine. It's just that you did a lot of unnecessary work, that's all. Now, for these three, the moments, we're going to use the special formulas. N times pi for the expected value. Whoops. No, we don't want that. So remember, there are 4 trials with a 0.4 probability. So in other words, whenever we repeat this experiment, on average, we expect to get 1.6 purple M&Ms. All right. The variance as you recall, the special formula is n times pi times 1 minus pi. Okay. So you're going to have 4 times 0.4 times 0.6, which is 0.96. And then finally, of course, the standard deviation is simply the square root . Which is approximately equal to 0.98. That's close enough. Oh, and that problem is done. Nice. Now the next one is very, very similar. It's another binomial problem. Of course, more practice is always good. So let's take a look at it. We have 10% of all people are left-handed by assumption. In a statistics class with 9 students, calculate the probability of the following number of lefties. Okay, so n is 9 and pi is 0.10. So we've got some probabilities to calculate, which again, we can do 2 different ways. We can use the formula. Okay, because, well, let me just repeat the formula right here. All right, so you can see the first two terms are just 1. 0.9 to the 9th is, let's see, 0.3874 approximately. So we're done. And now we'll try the same thing with the formulas on the calculator. All right, let me just go grab those for a second. There's no point retyping all of this stuff over and over again. All right, so this time we have 9 trials with a 0.1% chance of success. X is 0, so let's try this one. So no lefties. It's a fairly high probability. It's this. It's not exactly the same. No, it is. It's close enough. 3874. It's almost identical. Very good. How about 2? All right. Well, it's not too much of a stretch. So those terms are, let's see. Mm-hmm. So the 9 choose 2 is 36. Point 1 squared should be 0.01. And then 0.9 to the 7th is 4783. Point 1722. Okay, now again, we can do the same thing with the calculator. You only have to make one change. The X value is 2. Let me just confirm that. Okay. And yes, it is. No, wait a minute. Something's not right. What happened? All right, let me try it again. Oh, no, I must have hit the wrong key. It's 0.1722. Perfect. And then once again, we have at least 1. Well, that wasn't very original of me, but so 0 had a probability of 3874, which means it must be 6126. Okay. Now we can do the moments. Expected number of lefties, n times pi. is 9 times 0.1. So 0.9 is our expected value. The variance is n times pi times 1 minus pi. Actually, let me just borrow this. All right, so we have 9 times 0.1 times 0.9, which brings it up to 0.81. And then finally, the standard deviation is going to be the square root of that. And just by a ridiculous coincidence, it's the same as the expected value. You don't see that very often. All right, now what's coming up next? Now we're running out of time here. Part 11, this is a Poisson problem because it involves customers going to a bank every hour. Just remember that. These are probabilities, just straight ahead probabilities for the standard normal distribution. These are probabilities for the normal but not standard normal distribution. And this is the normal approximation of the binomial. So actually, we don't really have that much further to go. We should be able to knock this off in 15, 20 minutes tomorrow, and then we can carry on with chapter 9, which we kind of just barely started. Okay, that's good. We don't want to run out of time, that's for sure, because it's hard to imagine, but next week is our last week. I know, it's hard to imagine. It just goes so fast, but that means we'll be ready for the midterm. And we'll be ready to do a large chunk of chapter 9. And then remember, chapter 10 is the last problem, the last chapter rather, but we do also have to review for the final next week. So we don't just have to finish chapter 10, we also have to review. So I think we'll just about make it. I think the timing is just right. We're right on track here. So I'll post all these results. Right now, we're up to 4. Okay, remember I had to break it up into 4 pieces, so you won't be horrified when you see it. So you can go through and review tonight if you want to, and then we'll finish this up tomorrow. All right, and if you have any questions, you can let me know, and I'll see you all tomorrow.